A steel beam can hold up an entire skyscraper. Yet it starts as reddish-brown rock pulled straight out of the ground. It looks like the toughest material on the planet, but for a few brief minutes during production, it's actually a glowing liquid hotter than lava. It bends, stretches, and snaps back into shape. Yet the exact same raw ingredients could just as easily become something as brittle as glass. And somehow, the strength of every bridge, skyscraper, and car on the road comes down to controlling something invisible: the exact amount of carbon trapped inside the metal. That shouldn't be this delicate for something this strong. So how do factories turn iron ore, a rock most people would walk past without noticing, into a material strong enough to hold up entire cities at a scale of over 1 billion tons every single year? Let's step inside and find out. Almost nobody has seen steel before it's steel. It doesn't start as metal at all. It starts as rock, mixed with impurities, buried underground for millions of years. By the time it leaves the factory, it will have been melted at temperatures hotter than most volcanic lava, purified, reshaped, and cooled multiple times. And not one part of the original rock will look anything like where it began. What's stranger still is that the entire transformation from solid rock to a finished, load-bearing beam can happen inside a single connected chain of factories, often located right next to each other, specifically so the metal never has to fully cool down between stages. Steel begins at a mine, where iron ore, a reddish rock containing iron oxide, is blasted loose from the earth and crushed down into smaller chunks. This raw ore isn't pure iron. It's tangled together with oxygen and other minerals, which means it has to be chemically separated before it can become anything useful. Alongside the iron ore, 2 other raw materials make the trip to the steel mill: coal, which gets baked into a purified fuel called coke, and limestone, which will later help pull impurities out of the melted metal. Coal doesn't go into the furnace directly. It's first heated in massive ovens without oxygen present, a process that can take up to 18 hours and drives off nearly all the coal's volatile chemicals, leaving behind a hard, carbon-rich fuel that burns hotter and cleaner than raw coal ever could. All 3 materials, ore, coke, and limestone, arrive by rail or ship in staggering quantities, since producing a single ton of steel typically requires more than 1.5 tons of raw material to start. The iron ore, coke, and limestone are loaded into the top of a blast furnace, a structure that can stand taller than a 15-story building. Superheated air is blasted in from the bottom at temperatures exceeding 2,000 degrees Celsius, causing the coke to burn and strip the oxygen away from the iron ore. Over several hours, as the materials slowly descend through the furnace, the iron melts and separates from the rock, pooling at the bottom as a molten liquid called pig iron, glowing bright orange-white and hot enough to instantly vaporize water. The limestone plays its own quiet role here too, melting and binding together with leftover rock impurities to form a floating layer called slag, which sits on top of the molten iron and gets skimmed off separately, almost like fat rising to the top of a broth. Pig iron on its own is too brittle to be useful. It still contains too much carbon and other impurities. This molten metal is transferred into a converter, either a basic oxygen furnace or an electric arc furnace, depending on the mill, where pure oxygen is blasted directly into the liquid metal. The oxygen reacts with the excess carbon and burns it away almost instantly, in a process so fast that a batch of molten metal can be refined into steel in under 20 minutes. Once the excess carbon is burned off, engineers add back a precisely measured amount, often less than 0.5% of the total weight, along with other elements like manganese, chromium, or nickel, depending on what kind of steel is being made. Stainless steel, for example, gets a heavy dose of chromium, which reacts with oxygen in the air to form an invisible protective layer that stops rust before it can start. Tool steel gets extra carbon and sometimes tungsten, hardening it enough to cut through other metals without dulling. This single adjustment is what separates flexible, bendable steel from the hard, rigid steel used in tools and blades. Too much carbon and the metal becomes brittle enough to shatter. Too little, and it stays too soft to hold its shape under weight. The refined molten steel, now a specific alloy recipe rather than raw iron, is poured into a continuous casting machine. Instead of being poured into individual molds one at a time, the liquid metal flows continuously through a water-cooled mold, solidifying on the outside within seconds while the core stays molten for longer, forming a long, glowing slab that moves without ever fully stopping. The solidified but still red-hot slab passes through a series of massive rollers that squeeze it thinner and longer with every pass, similar to rolling dough, except each roller can apply thousands of tons of pressure. Depending on the final product, the steel might be rolled into thin sheets for car panels, thick beams for construction, or long rods for rebar. This step alone can stretch a single slab of steel to many times its original length in a matter of minutes, and the entire slab stays glowing orange throughout, since it needs to remain above roughly 900 degrees Celsius for the rollers to reshape it without cracking the metal. As the steel exits the rolling stands, it's cooled using controlled water sprays, a process that has to be timed precisely. Cooling too fast can make the steel brittle, while cooling too slowly can leave it too soft. Once cooled to a workable temperature, the steel is cut into standard lengths using rotating shears that can slice through a moving beam without ever stopping the line. Before any batch leaves the mill, samples are pulled and tested for tensile strength, hardness, and chemical composition, often by physically pulling a sample bar apart in a machine until it snaps, just to confirm exactly how much force it can withstand before failing. Sensors along the production line also scan for internal cracks or inconsistencies invisible to the naked eye, using techniques like ultrasonic testing, which sends sound waves through the metal and listens for how they bounce back. Any hidden void or crack reflects the sound differently than solid steel does, flagging a defect long before it would ever be visible to a human eye. By the time a single batch has gone from raw ore to a finished tested beam, it has been heated past 2000 degrees Celsius, cooled, reheated, reshaped, and cooled again. In the entire process, from the moment ore enters the blast furnace to the moment a finished beam is stamped and ready to ship, can be completed in under a day. Here's the detail that surprises almost everyone. The difference between a soft, bendable steel wire and a hard, snap-resistant steel blade often comes down to less than 1% of carbon content, an amount so small that a single ton of steel might contain only a few pounds of it. That tiny fraction of carbon is the entire reason a paperclip bends instead of breaking, while a knife blade holds an edge instead of folding. Engineers actually classify steel almost entirely around this one number. Low-carbon steel below roughly 0.3% carbon stays soft and easy to bend. Medium carbon steel around 0.3% to 0.6% balances. Strength with flexibility for things like axles and gears. And high carbon steel above 0.6% becomes hard enough for blades and springs at the cost of becoming more brittle. And almost none of the raw material actually goes to waste. The gases released during the blast furnace process are captured and burned to help power other parts of the mill, and leftover steel scraps from cutting and shaping are melted back down and fed into future batches. Modern steel mills routinely produce new steel using more recycled scrap metal than freshly mined ore, meaning a beam holding up a building today might contain steel that was once part of a car, a bridge, or an appliance decades earlier. Unlike some materials that degrade every time they're recycled, steel can be melted down and reused indefinitely without losing its strength, which is part of why it remains one of the most recycled materials on the planet. Once cut, cooled, and tested, the finished steel is coated if needed. Some products get a protective zinc layer through a process called galvanizing, which prevents rust by giving the iron underneath a sacrificial metal to corrode first instead. Others receive a coat of paint, oil, or a polished finish, depending on whether the steel is headed for outdoor construction, indoor machinery, or consumer products. Once finished, the steel is bundled, labeled, and loaded for shipment. From there, it heads to construction sites, factories, and shipyards, where it becomes the literal framework holding up buildings, vehicles, and machines most of us interact with every single day without ever thinking about the rock it once was. A single steel mill running continuously can turn out several million tons of finished product in a year. Enough steel to frame thousands of buildings from a raw material that not long before was just reddish dust sitting in the ground. That's how a reddish rock pulled out of the ground, melted past 2,000 degrees Celsius, stripped of its impurities, and given back a carefully measured pinch of carbon, becomes the steel beam holding up the building you might be sitting in right now. Strength at this scale isn't an accident. It's the result of getting one tiny percentage exactly right every single time, in a process that starts with dust and ends with something strong enough to hold a city together. Until now.